Okay. Yeah, the slides are available on Luminous. Yeah. I think, yeah, it should be there. I uploaded it this morning. Okay. Okay, we're still waiting for a couple of students. So for those online, maybe 1 more minute. This is the e-open house session for designing intelligent edge computing. And we'll take about 45 minutes. Not all of them is lectures. We'll also show you a little bit about our workshops. Okay, so I'm gonna start. So you cannot see the students here because I have the camera off, but there's roughly about 11 of them in the classroom and about, I think 40 people. 40 people online. Welcome to Designing Intelligent Edge Computing. This is a short taster class. Usually our classes are 1 whole day, and this one is only about 1 hour. So it's just to give you a taste. Okay. And before I start, let me introduce myself. I am Lisa Ong. I'm a lecturer at Institute of System Science, and I teach machine learning and edge computing. I mostly teach machine learning, so a lot of my classes are machine learning heavy. I teach corporate clients. Sorry, I teach executive education as well as MTech. Okay, I'm just going to go through a few slides and we'll see. If you have any questions, please post them on the chat. I think we have a couple of us from ISS who can help to moderate. This way, everybody will be able to go through the content sooner. Okay, thank you. So, a little bit about ISS before we start. Just in case you are not familiar with ISS, we are part of NUS. We are a school in MUS. Our vision and mission is to enable digital economy and develop digital talent. So we have a few areas, a few trusts. We do executive education, so short courses of 3 days, 4 days, and more. We also do a graduate program. Currently, you are in this class, which is a combination. We actually have about 8 MTech students taking our Masters of Technology in Software Engineering. And we have 3 participants who are joining the class as a part of the executive education. So we have a combination. We run our classes streamlined so that participants of different programs can also be in the same class. We also do industry engagement, career services and counseling, and applied research. So a little bit more about our practice-based education, which is what you are experiencing here today. We do graduate programs. We have a few programs. We have a graduate diploma in systems analyst, which is for software, those aspiring to go into IT and software, non-IT people. It is a 1-year program with internship. And then where you learn about software development, object-oriented development, and you do basically an internship and a lot of practice projects. We have 4 Masters of Technology degrees. Currently, the one that we're in is software engineering, but we also have in AI, in business analytics, and digital leadership. So the master's programs also run about 1 year, and then they have capstone and internships. So on the right-hand side, we have executive education, which is basically our short courses. A lot of these courses in EE also overlap with masters. Basically, there are certain courses that can be run in both programs, and we just designate different learning pathways. So for example, today's course is also part of the software systems executive education group. So you can actually come in and take this class for about 4 days full-time without signing up for a master's degree. Okay. At ISS, we focus on giving flexible learning pathways. So we have, you can take courses that stack up to certificates, and the certificates can stack up to a diploma. And after that, certificates can also stack up to a master's degree. So the difference between these 2 certificates are basically different levels. So a graduate diploma cert and a master's degree cert are different levels of advancement. But the same idea, you still take courses and add a project and becomes a certificate. So here's an example of one of the learning pathways. Currently, our programs in, this example is a Masters of Technology degree in AI. Okay. Currently, the verticals are the certificates. And if you take these first 2 sets and add on to 2 specialist sets, you can actually create a degree. So the verticals contain little boxes, and these are the courses. For example, if I want to do pattern recognition systems, I can take these 3 courses. Once I've completed the 3 courses, I will do a group project. Basically, it runs about 4 months, even though it says 10 days. It's just 10 days of effort. And in a team of 3 or 4, that's about 30 days. So it's a pretty substantial project. Once this is done and there is a final exam, a written exam, you can get a graduate certificate. So if you repeat the process for other certificates, you can combine them and get a degree. The degree doesn't require taking a capstone project and to basically complete the degree. More information is available in this link. Okay, so I'm going to start the lecture now. As we have students in class as well, please try to keep your noise level minimum. And you can always ask through Zoom's chat function. I will be taking questions towards the end so that we will not interrupt the flow and help us complete an e-feedback form. Okay, so I will flash this later on again so that we don't have to keep this on the screen. Okay, so I'll come back to this slide. Maybe I'll just move it to the end and make sure that it's there. Okay, okay, so let's start the class. Okay, so today's topic is going to be on online learning on edge devices. So a little bit of background on this class. Is actually a 4-day class. So we are on day 4, which is the final day. And the first 3 days, we learn about orchestration, basically running different programs on different configurations of edge devices. I will give an example of edge device later. And then we looked into what can you run on these devices, including machine learning algorithms and other types of learning algorithms. Today's topic will be how to enhance the machine learning algorithm so that it can update itself on the device. So this concept is known as online learning. So what is online learning? Since we have people who are joining us for the first time, I will do a little bit of explanation on the terms. Start with an initial model. So initial model means a machine learning model, which is like a program, an algorithm that solves basically produces a prediction. You give it input data and then it gives a prediction. For example, if I'm trying to predict if it will rain tomorrow, I will get input data such as yesterday's, whether it rained yesterday and the temperature of today. So these 2 data fields, I pass it into the model, the algorithm, it will predict whether it will rain tomorrow. So the prediction is basically a guess, which is probability based. So it may say 50% chance of rain, and that is similar to a prediction done by a someone predicting the weather. So initial model, online learning presumes that we always have an initial model. So basically we have already trained something. So we are not starting from scratch. We can start from scratch, but it will be a little bit slower to train because what we do with online learning is we use a slightly more conservative strategy to update the model to make it more accurate. So the conservative strategy takes a little longer. Okay, so usually we will actually pre-train the model with a faster strategy, a more aggressive strategy, and then get something that actually already works quite well. And now we want to refine it in the field. So the refinement is done on the device. So what do we do with the refinement? So for each time step, we will first have to get a prediction. So we have to get something from the model. We have to ask it, what currently, is it going to rain tomorrow? And then, of course, you may not know whether it's going to rain tomorrow or not. So you may not be able to compute this thing called the loss, which is the error, right? Let's suppose I change my model, and instead of predicting whether it is going to rain tomorrow, I just predict the type of, whether I am looking at a picture of a cat, okay, cat or dog, right? C-A-T, cat. So if I'm looking at a picture, is the picture showing me a cat? I have the answer, right? I can actually see the picture and it tells me, okay, this is a cat. So I can decide based on the prediction output from the model, whether or not the model is right or wrong. So that is the idea of loss, right? So if I am correct, so if the model says cat and the picture is actually for a cat, then loss will be 0, right? Means there's no error. But if the picture is of a cat and the prediction is of a car, so completely wrong, then loss will be something high, like 1, okay? So this concept is basically a way to provide updates to the model, to refine the model. We want to know how much error it has so that we can progressively change the model, the algorithm, so that the loss will get smaller and smaller, right? So it is an iterative process. So next time we maybe will pass it a picture of a dog and see whether it gets dog correctly. So we'll do this for quite a few iterations, okay? So in offline training, which is training on, not on the device, but in, let's say, on the cloud, we will do all the training first, then we will test, right? So everything is done in two separate stages, okay? So in this case, when we do this training, we will feed it pictures of cats and dogs and compute the loss and refine the model, but everything is done in one go without, once we will finish, we will stop, right? We stop training. So that's called offline, right? Because the model is trained offline. And then we'll do the testing with the model that is already created, okay? So online, in contrast, is done stepwise. So instead of training everything, then testing everything, so one shot, you will do step by step, okay? So we do a step, the step can be maybe 10 pictures. We train, we pass it 10 pictures, we get the loss. We say, oh, okay, model is a bit wrong here, let's change it, okay? So we'll train it and then we'll test it with another 10 pictures. We compute, okay, is this model doing well? Still doing well? No problem. We'll continue training. Note that the tests can be with some independent test set to make sure that training doesn't cause the model to go haywire, okay? So the reason why we have train and test in machine learning is we want to make sure that it's independent verification of the model, okay? So that's why usually we will talk about training to update the model and testing to get the verification. Training updates the model. So in case you are confused, training is where the model is refined, right? So I'll just make a note here, training, right? So test is where most of the time we do the computation of the loss, okay? So note that in offline training, we don't refine the model. The model is done, that's it, right? But online training, we actually have a way to update it progressively and try to make sure it doesn't go too far away, okay? So one of the concepts of online learning is to make sure we don't go too far away. So this is the concept of regret. Okay. So regret means that, when you think about regretting something, right, it's something you shouldn't have done, right? So I shouldn't have changed to, I shouldn't have eaten this for lunch because now I feel bad, or I shouldn't have said this, right? Same thing. So the historical model that was trained and the current one that you have been slowly changing, there sometimes is a gap, right? Because maybe you've gone too far, right? Maybe you changed it too much and the original one was better. So what we do here is this concept of regret. Don't worry too much about this equation. What it's saying is basically the difference between all the updated models and the best one. Okay, minimum. Usually when you have a sign like minimum like that, it means that it's a best, either the lowest loss or the highest accuracy. Okay, so in this case, it could probably be the lowest loss model, okay, against what we have been updating. Okay, so the goal is, of course, to minimize the gap, right? We don't want to go too far away from what our best model is. So in online learning algorithms, they try to minimize that gap. Okay, and how do they do that? They also have tests to verify that we are still providing the model that works in our previous training set. Okay, so what I mean by that is, in here, right, the testing here is done to make sure that the model is working well, right? So when we compute the loss, we also try to make sure that it's still not it's still not as too bad, right? It's still in line with the current best historical model. So we will have a few statistics that we have to keep track of. Okay, even though I didn't show it here, what we have is we also have the historical best loss, right, so far, and then we also have the current loss. So we have to make sure that the current loss doesn't go too far away from the historical loss. Okay, that's the idea of regret. The historical loss, the one that we had before we started changing the model, shouldn't be too far away, right, from what we have right now. Okay. In practice, we don't implement this equation. This is just to give you the concept of regret. In practice, we actually use built-in algorithms like gradient descent. Okay, so gradient descent is one of the algorithms that we use for training neural networks. Basically, it's a way to change the weights. In this case, the weights are theta. Okay, uh, so that we can minimize loss. So this equation looks very complicated. What it does is basically this guy theta is being changed. Okay, theta equals something, right? So theta is being changed. So this thing is getting new values. What new values is it getting? It's getting its old value minus some big chunk of thing, right? So I like to call this like the progressive update for the weights, the progressive update that we are putting into the model. It is quantified this way because we are talking about changes to minimize loss. Okay, so J is loss, which is the error. This upside down triangle is just the gradient. So it's like the the rate of change of the loss. Okay, so the rate of change of J multiplied by some number, right, will be used to change the weights. Okay, this is a sort of a standard formulation of this thing called gradient descent. Okay, basically it's standard because the theory is that if this loss goes higher, right, we want to change this in the opposite direction. Okay, as the loss. Okay, so maybe this is a good time to show example of gradient descent because I don't have it here. So let me see if I have it here. No, I don't. Okay, so let me just show you. Okay, so I'm not sure you have seen this before. So that's good. Let's do. There's a lot of diagrams for this for gradient descent. Standard ones look like this. Okay, so if you Google gradient descent, you see like things like there's a U shape and then there's a winner or there's a minimum. Okay, so let me just take this one as an example. Okay, the good thing about machine learning is there's a lot of different helpful tutorials out there, almost too much. Okay, So I just want to use that curve to sort of explain the loss and the direction. Okay, so this is the curve. Okay, so this J thing is the loss, and the W is the weights. So this is the parameters of the machine learning model, right? So for example, it will help. It's used to predict whether it will whether my picture is a cat or dog. Okay, so I have some values of W, will predict whether it's cat or dog. At this minimum value, it's actually predicting cat, so it's good. It's minimum. Okay, so it's lowest error. Then at this value up here and up here is predicting, here maybe predicting kangaroo, here maybe predicting car. So wrong, right? So the loss is higher up here. So what happens is, if you notice, right, the minimum point is at the flattest spot, gradient is 0. Okay, so if you remember vaguely calculus, gradient is 0, means that there's no slope, right? It's flat. Then gradient is negative, means it's on the left-hand side. Then gradient is positive, is the right-hand side. Okay, if you vaguely remember, it's not really required for to know to do machine learning, but it's helpful. So what's happening is, as cost decreases, right, negative gradient, right? So you see this curve. If I follow this blue line, cost is coming down, J is coming down. This is a higher value, this is a lower value, right? So notice what happens to W. So if I move from here down, W is going up, bigger, right? So that means if I want cost in a negative gradient, right, I need to change W to be bigger. W needs to go bigger when my gradient is negative, right? And then on the right-hand side, gradient is positive, okay, because positive is this direction, right, from calculus, okay? So gradient of this guy is positive, right? So W needs to come down. So you notice that the change, W direction is opposite to the sign of the gradient, okay? So let me repeat, the direction of W, which W to move to get to this point, which is our best part, is opposite to the direction of the gradient. Positive gradient, W go down. Negative gradient, W go up, right? See, W is moving this way, okay? So this W, right, will change how our model works, right? Because if a W is lousy, like up here, then all the cat pictures will be predicted as kangaroo. If W is good, then we'll get the good answer, okay? So it's just a very layman's way of explaining it, but this concept is captured in this, not this equation, okay? So now this value is just how much do we change? Maybe we don't want to move too much, we want to slowly change, okay? So understanding this is helpful in understanding the next equation, okay? So the next equation, so notice that I say here, earlier we say we want to minimize regret, right? We don't want to go too far. This algorithm doesn't do that, okay? It's a standard algorithm for training neural networks, but it doesn't minimize regret. So we cannot really use it. I mean, if we use it for online learning, we will not achieve our goals. It can be done, anything can be done in practice, but it will not be as useful, okay? So it will not be as conservative. So what do people do? They modify this equation. What do? They take this n, oh, sorry, I don't know how to pronounce this. This, what is it? Class, anyone knows? Eta? Eta. Okay, let's call this eta. This n thing with the tail. This eta, and they change this. So they make it adjust. Okay, adjust according to regret. Okay, so what they do is, yeah, you see this eta earlier? Okay, this G thing is still the same as before, roughly. Okay, this is the gradient. So you can ignore this. Just look at this eta. Now you divide by something. Okay, so this is adjustable. So now we will adjust the rate according to our sum of squares of gradient. Okay, so basically people have figured out that they can modify this dynamically. Okay, so just know that this is dynamic. Okay, so they can modify this dynamically so that we can minimize regret. Okay, because as we change the weights, right, we will also change the gradient function. Okay, this guy will change. So we don't want this to be static. We want this to be sort of adjusting as this changes. Okay, I just spit out a lot of theory. So it's just for your background to know that there are certain algorithms that you should choose when you do online learning. Okay, AdaGrad, There's a lot, Adam also, but this one I find is the easiest to understand if you understand the one before lah. Okay. Any questions from the class? No, can ask later. Okay, so I will skip this slide. I mean, it's just really to support the undergrad. It's not really needed to in depth for edge computing and deploying on Raspberry Pis and all that. But it will explain at least how a little bit more detail on this. Okay, so I'll skip this. We don't want to stare at equations too long. Okay. So there's other enhancements, other algorithms, ada grad, ada delta, and Adam. For example, you can change this, formulate it somewhat differently. So notice the similar thing again. Okay, this is defined as this equation. Okay, which is basically the previous history with some current gradient, and the beta here is just a slider. So imagine that beta is a number less than 1. So for example, if beta 2, this guy here is 0.3, then 1 minus beta 2 is 0.7, right? So if beta 2 is 0.3, right, and this is 0.7, imagine this is sliding between a 0 and 1 scale. Okay, on left-hand side is this. I want 30%, I want this, and 70%, I want this. So it's just, at the end of the day, it's just balancing different parameters and incorporating them into the equation and somehow making the equation dynamic. Okay, that's really what a lot of these scary looking equations do lah. See here, another slider. It's just balancing the history with some current gradient so that you can, why do you care about history? Class in my class. Any guess? Why do you care about history? Yeah, so correct. Yeah, so you're doing some kind of optimization. You're trying to get the pattern, but you're also trying to minimize regret, right? So regret is about history. Okay, so you're trying to minimize regret. So you're trying to keep into account of what happened before. Okay. Okay. So okay, this is the last technical slide, I think. Yeah. So TensorFlow Keras implementations. Luckily, you don't have to implement this by hand. First of all, it's very difficult. I mean, it's time consuming. And second of all, these have to be quite optimized because you are using this to train with a lot of data, many iterations. So you want an optimized implementation. So that's where we use TensorFlow. TensorFlow/Keras. So this slide was for Keras, but since then Keras has become part of TensorFlow. They still preserve this, so you can still use this. There's some parameters you will tune, like how fast the initial rate. This is the eta or mu, right? And then how to change, how to decay. So these things will take a little bit of study and experimentation to use, but some of them can tune themselves. So this one in particular, I would recommend, if you don't know anything, just use this one. He will self-tune. You don't have to change all this. In fact, the paper will recommend, please use this. So I don't know why they give this for you. Maybe if you are advanced, you want to tweak them and outside of the research paper. But this one you can just use as is without change. Okay, Adam. This is why Adam is very popular. Okay, so to take a step back. So all these things, what are these for? These are actually used to update the model along the way, right? So we've gone into some detail of all the different ways to run the optimizers because we will want to understand that this can help you. These are sort of recommended to use if you have a current model, you put it on an edge device like a Raspberry Pi and you want to update them. Be aware of what optimizer you use, okay? Because if you use the wrong one, your model can go quickly accumulate a lot of errors. Okay, that's the key takeaway. Okay, so more algorithms, not just machine. So what I covered was just neural networks, and neural networks can span a lot of applications. They can be many different types. But if you don't want to use a neural network, you can actually use some of these classical algorithms. Random forest, support vector machine, and k-means. So random forest is basically a group of decision trees. So it's just learning something that is a little bit more explainable, can be interpreted, okay, not as black box as neural networks, but you can actually update random forest online, okay. Takes a little bit of setup. It's not out of the box. Cool. Out of the box will be this guy, incremental SVM and mini batch k-means. And there's others. If you are not interested in neural networks, you can actually take a look at these as well. Okay? The idea is the same. You use the initial algorithm like SVM to train your model offline, then you put it on, deploy it, and then you use the incremental version to update. Okay. By the way, k-means is not supervised learning. It's clustering. So in case anyone caught this, this is if you want to do online learning clustering, is possible also. Okay. I don't know what the result will be though. Okay. It's a bit hard to do. Okay, so I'll just check if there's, okay. So it looks like we have about half an hour left. I will do the fun part now. So this topic is just an introduction to online learning, um, highlighting some of the issues and the algorithms to use. But what we want to do, actually, we want to apply it, right? So in our classes, what we do is we also have an afternoon of workshops. In this class, because it requires devices, I will actually not be able to let people online do this, but I will show you what it looks like. So hopefully you can see my camera. This is a webcam. Basically, it's pointing at my Raspberry Pi. So this is my Raspberry Pi 3. I have a rubber band here so it won't slide around, but it's a Raspberry Pi 3. Okay. And this is a device that has sensors on it. It's known as a microbit. Okay. It's built by BBC, the British Broadcasting Company, and they did a really phenomenal job. Okay. Because it is very widely available and it comes built in with sensors, it's very easy to program. So what we're going to do in the workshop is we're going to do gesture recognition using this. So for example, I can wave this. This is a gesture, right? So I'm going to mark the gesture and train it, right, on the cloud first. Then once I have the algorithm, I will put the algorithm here and I'll connect this guy to this, right? And then I'll continue doing my gesture and the model will update on my edge device, okay? So our class is all about getting things to run on these small little devices, different ways, limitations, and things like that, okay? So we will not spend so much time doing the workshop here because it's only for the people in the class, but I will at least walk through the code so that you get a flavor of it, okay? So in class, we will have basically, there's several Raspberry Pi 3s distributed. This is known as an edge device, which is just like a slightly more powerful IoT device. You can think of it as something that is small enough to deploy in many places, but not like a huge blade server. So you can run compute on it. You can run machine learning on it. You can run your own programs, and it will be sufficient to support the sensors. Then I have a BBC microbit, which includes my sensors. I will be using Google Colab, or we will be using Google Colab to train the model first in the cloud. Okay, so I'll show all these things, but first I'll just give you a highlight. First, you will record some gestures using the microbit. There is an accelerometer and there's compass heading in there, so we'll do that. Then we will go to the cloud. I'll show you how we train initial TensorFlow model. Okay, we'll open this notebook. Then after that, I may or may not have time to do this, but the idea is once you have the model, right, it's just a file. So you take the file and you put it on the Raspberry Pi, and then you run some code on the Raspberry Pi to continue training using the AdderGrad and all the other optimizers we talked about. Okay, so let's look at the first part. Okay, so let's look at the first part. Okay, so sorry, this part, the BBC microbit. Okay, and in class we have the handouts like this. So we will do this is what the class has. So step by step doing this, and basically they just follow the instructions. There's some exercises to do. So I'll just show you what happens. I have my microbit right now. Okay, right now it's connected not to the oops. not to the Pi, but there's a cable here. It's connected to my laptop. Okay. I will not show my laptop. Okay, maybe I will show my laptop. Okay, it's connected to my laptop. Okay, can see. Okay, so all right, just make everything lay out properly. Okay, so you just have to take it by faith. It's connected to my laptop, and then so I can. It's currently so if I look at device manager, which is how we find these devices, you see that there's a thing called USB serial device COM5. So it's connected to my laptop over USB, but using serial port. Okay, SERIAL serial port. So microbit is very handy to program because when I plug it in, right, see my machine on the left hand side, microbit is here already. Okay, so it's actually showing up in my PC. And to program it, right, all I'd have to do is drag and drop. Okay, so the students here in my current class will actually go, let's hide this for a sec. Okay, okay, let me check the chat for a second in case it's something urgent. Okay, we'll talk about that later. Okay, so let's hide floating controls. So here's a microbit editor. So it's actually an online editor. Okay, on their website microbit.org, they have an editor for a different language, but Python is the one that's very, I guess, that we're using today. So the students here will actually take this code and paste it here. Okay, and then this code, what does it do? It's running. It has a function that sends sensor data. Okay, and it's running this function in a loop. Okay, every 100 milliseconds. Okay, so it's running quite fast. Okay, every 0.1 second it will do it. So what does it do? It calls the accelerometer to get values from it. So this is actually talking to the microbit already. So let me show my microbit. Okay, it's talking to this guy, microbit. Okay, so there's a accelerometer in it somewhere here, I think. And then it will get the value from the accelerometer. Okay, and also the heading, the compass heading. Okay, so right here. Okay, so this code is just taking the accelerometer, unpacking it, okay, and putting the compass heading, including it. So this is just an array, okay, comma separated array. Okay. I also have this thing called button A is pressed. So button A, microbit comes with two buttons, A and B. Okay. So we can, not sure you can see, right? There's one here, I'm pressing one, okay, pressing the other one. Okay. So you can find more details about the microbit and its specs online, but these two buttons can be used as triggers. So this is why this is such a nice device, because it comes in with all these things already programmed. You don't have to do breadboards, and it's nice, easy to transfer and learn. Okay. So what it does is it will print whether button A is pressed, and then the X, Y, and Z coordinate, right? G, yes, accelerometer, not coordinate. G values, okay? And then it will also print a heading. So I'm just dumping the data out to a comma separated string, okay? So if I got to program it, I just do this, download a hex file, okay? So click download, and when I click it, okay, so continue. I want to make sure it downloads, okay? Okay, so if I click it, it should download, right? So there's a microbit 1 hex file, okay? Microbit 2, I click too many times, okay? So you only need one, okay? And what we see is the file, so 1 and 2, they are the same, right? So let's see how big they are. There's about 600K, okay? So what I do is I take this and I drag and drop to the microbit. So let me find my microbit somewhere. I have unplugged it, I think. Right. Up here. So it's here. So I'll just take this, right? Doesn't matter which one, they're the same. Copy the microbit, okay? Then as this is happening, you see that my microbit is actually flashing. Oops, too large. I've done something wrong. Okay, let's actually take this. Okay. Yes, let it finish copying first. Okay, so it finished copying. Okay, so now my microwave is flashing, right? It looks like fancy LED lights, like disco light like that. Okay, so what happens is I have the compass on, so I need to actually calibrate the compass. Okay, so to calibrate the compass, I will try not to make you dizzy. I just need to fill in all the buttons. Okay, so I'm doing this game where I tilt this. Okay. Compass calibration is usually needed because magnetometer is very sensitive, right? It will drift. Okay. Compass uses the magnetic field, right? So usually you will, if you use any device that has compass, you'll be asked to calibrate it. Otherwise, it's not a very good one. Okay. So it says tilt, so I didn't tilt fast enough. Okay. Tilt to fill something, screen. Yeah, so this code I didn't write. It's part of, see, I have one more box. Okay, let's make sure. I'll just do it without showing you. Come on, fill the screen. Okay, full screen. Okay, now full screen, done. Okay, now it's finished. Okay, so it's calibrated. Now give me a smiley face, happy. Okay, so it's actually program. Okay, so now I will go connect, step 2. Okay, I will go connect it. Okay, and I will collect data. Okay, so I'm in this part, acquire data. Okay, so we will try to share this. We'll see if we can share this handout. It may not help you much if you are online because unless you have the devices, but just to give you an idea. So I have my workspace to collect data. Okay, I have a Python script to acquire data. So let me run it first. Okay, okay. Before I do that, I need to modify it. Okay, so I have to open here. So this is acquire data. There is a field here. I didn't make this programmable. It's just, didn't have time or lazy. So I put the you have to change the COM port. I think default is COM3. Okay. So to find your COM port, you just go to device manager and then you like look, and you see, oh, this one, COM5. Okay, it needs to match. Otherwise, it will try to connect to this. I don't know what it would do. Okay. So this is the connection on the PC. Okay, my machine. Okay, so I set the baud rate because it's 0. I will output a file called data1 CSV. Okay, and then I will just acquire the data. Okay, so I have some code that I'm not showing here. Maybe I'll briefly show it. It's not that hard. This is all on GitHub, by the way. So we'll send links to it later. So I think I put it. I need to find where I put it. Serial to file run. Oh no, this one doesn't have anything. This one is just using the built-in serial IO. So it's just taking the output from the serial port and just dumping it. There's no special code. Okay, this is just reading from a serial port and dumping it to a file. Okay, so let's run it. Okay, to show you what I mean. So I run this Python script. Okay, now you see that there's data, false, and then some values. So this is X, Y, Z, and heading. So I'm going to press button A. You should see it change. See, button A is pressed. You see there's some true there. True, 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 true. Okay, I keep pressing it. Now it's true. I let go. It's false. True. So what are we doing here? So we are going to use this true and false as our labels. So when I perform the gesture, let's say my gesture, right? I decide my gesture is like that, up and down. I'm going to mark that this is my gesture. So I need some way to label to mark that these readings, right, sensor readings are for the gesture versus not for the gesture. Okay, this is so that when I train the model, when I pass the data in, it can distinguish what sensor data corresponds to my gesture and what is just rubbish, right? You need that because everything, you need to be able to distinguish. Okay, the whole goal of machine learning is to be able to tell between things, right? Be able to distinguish whether this data is true or false, right? So for example, if this is my gesture, so because I caused it to take too long, I'll run it again. Okay, come on. Control C already. Still cannot. Okay, so let me just get it back. But anyway, I'll see if I can get it running because it's stuck. Yeah. So there's some, because we are working with real devices, we get some interesting behaviors. But if you imagine that during this time, right, when I press the button, I'm actually doing my gesture, right? So this is, I press the button to indicate it. And then later on, when I'm not doing my gesture earlier on, I say I don't press the button. So that later when we learn the model, right, it will know, okay, this answer should be false. This answer should be true, right? This is for not gesture. This is for gesture. Okay. Okay. So that is that. So this was saved to a file. I hope I have the file open. Maybe not. Something like that. The file will look something like that. Okay. Maybe I didn't save. Yeah. There's some line endings because of the way serial port works, but we will handle that in our data thing. So this is the data that we will use to train. Okay. So it's just a bunch of numbers. So in the lab, in the workshop, the students will actually run and do the gestures a few times so that they have enough data. Okay, this is too little. Only 200 rows not enough. You need maybe about a couple thousand, which is very, very easy to generate. Okay, so that's the data collection. So now we will go to the training part. Okay, so training part will be using a notebook called Edge Online Learning. Okay, right? So this is the guy. So I walk through it. Um, so the outline is we'll load the data set. There's some exercise there to inspect. Then we'll prepare it for training. We'll train, and then we'll prepare it for deployment. Okay. So the simple model basically is just the model that will take in the data that we collected and just train a binary gesture detector. Okay. So this is running on Google's environment. It's a free cloud training resources, right? You can actually select it to run on GPU if you like, for example, yeah, for free. Okay. So let me just go ahead and do that. I haven't run it yet, so I can switch. And then it will install some versions, okay, some libraries, and then run. So I can run this. So basically, every cell you just go ahead and run, right? But in the interest of time, I will just give you a flavor of what we do. So we will use some libraries from sklearn to clean the data, and we'll do some TensorFlow modeling. Okay. At this point of the class, the students have already done one workshop that has used a bit of this. So they are a little bit more familiar than the ones online, but than the listeners online, but it's still quite a lot of learning. Okay. So here is where we load the data. See, here's my example. In order for this to work, this data, right, needs to be available for collab. So when you go to the file step, you need to upload the data. Okay? Right now it doesn't have it, right? So let's say if I upload the data, so if I go to my desk, where did I do? I think I did here. Yeah, day 4. You take, yeah. So and then it says uploaded pictures will get deleted when the runtime is recycled, right? Uh, Files, because this is running in Google's cloud, right? So this machine is recycled after 6 hours. Okay, so this is where my data is here already. So notice I have different file name, so I have to change this, and then it will load lah. Okay, I will not load this here, but basically it's loading what we saw earlier. Okay, true, false. Okay, then I do some. This is actually loaded online, so that we can train. Okay, then we'll do some processing, plot the data. It looks like this, just to inspect it. Okay. Okay, so I'll skip this part. Then there's some exercises just to plot it, because everybody's data will look different. So we'll just have them submit theirs, okay, their gestures. Okay. You notice that there's a bump here, up here. This is where we press the button. So this indicates that there's a gesture, no gesture, right? So I did this gesture about 20 times. Different size, different frequencies. It's good to have different data. Okay, you don't want to have all the same, so you can at least make sure in real life it will be more easy to predict whether it's this or not. Okay, so it's just to show that. Okay, so I'll skip to then there's some processing, preparing for training. I'll skip this part. It requires a little bit of knowledge of machine learning, which we don't have time to cover here. But really, we're just doing basic training of the data. So I'll go to the model real quick. Okay. training. Okay, so here's the model. Basically, it's a uh, convolution layer and then into dense. Okay, so the students have already done a model that looks similar like that before. So what this is actually just looking at windows of three at a time, and then it's just doing a sliding window. Okay, it's a sliding window multiplied by some numbers. So you slide your window along the data. Okay, so what I mean is, if I go back here, see I have this data, not this data, but the one above. Come on, this right? This is my data, right? I have 1, 2, 3, 4, 4 rows, 4 sequences. So imagine I have a sliding window that I will just move along the data. Da, 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 da. So I will learn windows of it. Okay. So windows is important because we are talking about uh, gesture, right? Gesture is not just one point, it's a sequence. Okay. Okay. So that's the window. Then after that, this is just a classifier, which means that it will take the window, slide it over, and it will try to do some mathematical operation to detect whether it's return whether it's 1 or 0. So the important point here is that the output is the same size as the binary, which is 1, right? So this value should be either 1 or 0. And then the input is not specified here, but it's actually our time steps and our features. So we'll look at 20 steps and 4 sensors. And then in the 20 steps, we will slide 3 at a time. Okay. So those are parameters. Okay. So long story short, we are fitting the model. This is still done where? This is still done offline. Okay. It's not running on the device yet. Okay. So it's still training offline. Suddenly my mouse is not working. Okay. So then this is the learning curve, which is basically how much error I'm getting. So the orange curve means that my test data is not doing as well as my training data because the error is higher. This is normal in machine learning because as the model gets trained longer and longer, it will start to learn, you start to memorize the training data. It will memorize it so much that it will just be so good about it, and it will not do well with things it hasn't seen before. Okay, so this is the notion of overfitting. Okay, anyway, some of these concepts are more require a little bit more study, but the idea is that you can actually get a model and you can put it, save it to a checkpoint and prepare it for deployment. Okay, so last part, preparing for deployment. So we have to save some things. We have to save the model checkpoint, which is just a snapshot of the model. We have to save how we pre-process the data. And we also have to save our test set. Okay, this is the test set. So going back to the slides, we have, we talked about this earlier. Okay, right? Train and test. So I'm keeping the test set. Right, validation is this. Right, I need to be able to, along the way, I need to check. Right, because as I'm updating it, right, I may not, my model may go haywire, it may go too far away. So I still need to keep the validation set. Okay. So the model, current model, or the initial model, right, is this guy, is this thing, the checkpoint and the preprocessor. So the concept of model is usually means both the algorithm and the code that is used to prepare your data so that the algorithm can work on it. So this I consider as a model. Okay. So model and test set, right? So this is our pre-trained model. And then I have some code to read and write from it that I test it locally. Okay. Okay, that part is not so super important. Okay, you will have a link to this notebook to look at it in detail. So let's go to the end of the web notebook to see what's going on. Yeah, this is just to test that I'm able to use it locally before I'm testing that I can also continue training here, but I don't really want to do it here. I want to do it on the Pi, right? So go back to my Raspberry Pi. Okay. So this is my Raspberry Pi. Okay. It's currently in the day 4 folder. Okay. So I have, let's see, let me follow the workshop. Okay. So in deployment, we will download it from Google Colab into the laptop, okay? Then transfer it to the Raspberry Pi and do online training, okay? Let me see if I can get that in 5 minutes, okay? So let me run the notebook. Run all. So I can run the whole thing, okay? And it will get me my files, okay? This data is not very good, so I don't expect my model to do well, right? So in general, for machine learning, your model work, how well your model works really depends on how good your data is. Okay. So this is going to take a little bit of time to run. Okay. Meanwhile, while I'm running it, I will just preload WinSCP, which is how I copy the files over. Okay, so you see it's running in the background. Okay, go away. Okay. So I will go to so this is my Raspberry Pi. Actually, the IP address is not this, but I will do new site. Okay. I have the IP address here. Here's my IP address. It's connected over Wi-Fi. Okay. All right. So put this guy, and then username, password. All good. Log in. Yes. It should prompt me. Okay. All our Raspberry Pis have pre-configured a password already. So this is my Raspberry Pi. Okay. So I go into the folder day4 RPI. Okay. So I haven't downloaded my thing yet. So you see my data is, my model is already here. This is the format used to store Keras and TensorFlow models. Okay, it's a binary format. See, the model is almost 1 megabyte large, and this is my data and preprocessor. So these two needs to be downloaded. So to download this, download and download. Okay, I'll download this as well because I may need it. Okay. So I have these three in my downloads folder. So I will go to my downloads folder. Okay, downloads folder. Okay, so where is it? Sort by date. Thank you. So I put this over. Okay, so it's transferring. Okay, now if I go back, maybe I only well, I'll just do it just in case. Thank you. Okay, so if I go back here and I go to the Pi folder, I will see my thing here, right? It's just transferred. Okay, Raspberry Pi, this is the data. So there's a script called incremental train that will train it. But before I do that, I need to connect the microbit to my Pi. Okay, so I'll just show that the screen. So microbit disconnected, connect to the Pi using USB. Okay, I'm cheating a bit here because in general, we don't actually physically connect these sensors in practice in real life to the device, because you will use things like Bluetooth and wireless, right? You don't expect there's always a cable running, but for reliability and for development, it's useful to have just direct USB connection. Okay, so I'm connecting the microbit to the Pi right here. Okay, so then I can just do my gesture and train. Okay, so it's completely standalone now, no more PC. Okay, so I've connected to it. I need to figure out what COM port it's connected to. So so there's instructions for this this guy. Okay, I know this because I've been using it for a while. Okay, so there's other COM ports here as well. But basically, when you unplug it, this is not there, and then when you plug it, it's there lah. Okay, but those things you can Google. Okay, so how to run this? Well, let's see. There's an explanation, trigger path. So switch on, see the path, keep it connected. So launch the Docker container. So what we do in our workshops is we use Docker to deploy different libraries to run on the Raspberry Pi, different environments. This is a useful way to deploy different configurations that we need on our daily workshops. Okay. The Docker file is basically quite straightforward. I'll just show. Okay, since you may not have seen it. Okay, this is a GitHub repo. I'll share the link, but basically it is a Docker container, right? Which has certain libraries. Okay, so instead of going in and manually installing on the Pi, I would just open this container, which already has some stuff pre-installed, like TensorFlow. Okay, I pull this from Docker Hub, which is a central Docker repository. Then I add these libraries, right? And I just do some testing on it to make sure this all works. But this environment with TensorFlow, Raspberry Pi, and the async IO for Zero is all included already preloaded. Okay, so it saves time for the students as well. So if I just go to this and do launch Docker, oops. So the same thing I just showed you is on the Raspberry Pi. Okay, I hope this works. So you see it's downloading from Docker Hub. Okay, so there's no other installation needed. It's going to pull the image. Okay. Huh? Takes a bit of time. Yeah. But I guess while we're waiting, I can see if I take questions. So where's my questions? First question from the class here. No questions. Okay. There's a chat room. Let's see. Okay, let's address some questions. Okay, so share the handouts. IVLE. Okay. GitHub link. Okay, so I'll post the GitHub link at least. Okay. So here's the GitHub link. Okay. So hi. Okay. And then sample data set like those. Yeah, the GitHub link should have a sample data set there. Okay. And then let's see. So this interface not very helpful. Keep scrolling up and down. So let's see. GitHub link device specs. Okay. So device specs. Microbit. So this is the Microbit webpage. You can find out device specs. Microbit here, you can also find out where to buy the Microbit. It's, I think, currently out of stock, but you may be able to find it. Okay, I'll know a friend with it. Okay, and then Raspberry Pi is just a Raspberry Pi 3. So Raspberry Pi 3. This also works with a Raspberry Pi 4. Okay. So you can find out more about this. Let's just do specs. Okay, we are using Model B Plus right now. But Raspberry Pi 3 has been superseded. 2 Pi 2B maybe not. You can try. I haven't tried that. The limitation will be whether or not it supports this architecture. You can try it. It's quite straightforward. All you have to do is put Docker. You can for older Pi try to install Docker. Okay, and then pull the container and try. Yeah. So if it works, it works. Okay. What features do we want to extract temporarily from this 1D-conf? So regarding this will be temporal features. So time-based, time window of 3. Okay, on the sensor data. Okay. So let me find a link for it. Time series sensor. It's a common technique used for if you don't want to deal with recurrent neural networks. Okay, so recurrent neural networks is also possible, but I find that it's a lot slower and doesn't work. It doesn't give me that much. A CNN just actually works just fine. Okay, so I use CNN because it is more is faster in small device, okay? Also faster to train. Those kind of things, RNNs tend to take a while and not supported as readily on small devices, okay? Like TensorFlow-like, okay? Okay, so go back to, I think I'll wrap up now. So go back to this, what's going on, let's see. We'll come back to this later. Yeah, as predicted, my students have been doing the workshop for a few weeks now. They know it takes a while to run. But ideally, basically what this will do is it will extract, okay? Yeah, it's still taking a while. It will extract this, and then what we do here, right? We launch the Docker container, okay? And then we just run this, okay? We do incremental train, which is a script, and then we specify the COM port, which is TTY-ACM0, okay? And then this will do the incremental train. So everything is wrapped up in scripts right now because it's a lot of coding to get it from scratch. So let me just show you what the code looks like. You can go on the GitHub repo, and then there's more details on the README file, what it looks like here also. The instructions are also here, okay? So if anything, you don't actually need the workshop handout. You can actually use this and play around with it, okay? So I think I will stop here. It's really not much point looking at this. So let's see if there's other questions. One more question. Is there any minimum for GDIP? Okay, this question probably we can address offline. Yeah, this one we can address offline. Yeah, it's a longer response. Okay. I don't necessarily represent GDIP in SA, so I need to make sure I can respond correctly. Okay. Let's see. There's a question. No, there's. Okay. So let me wrap up here. For MTech, I can answer for MTech. So for MTech SE, you do need programming experience. Yeah. Okay. Familiarity with Docker is a plus, but there is, I think there is a class that covers Docker. Okay. As always, I mean, these kind of things is nice to study on your own as well, play around with it. That's where you learn most. Okay, so let me wrap up. Okay, so maybe I'll send the link to the MTech SE program as well. Okay. Because there's a list of courses you can see which will help. So DevOps Engineering and Automation is the class that will cover Docker on the first cert of architecting smarts. Of the MTech. Okay, so let me send. There is a better link for this, so maybe I'll do it here. Do the stackable one. I'm assuming a lot of you are interested in stackable. So this one is the same content earlier I showed, but it has links to each class, so I find it useful. So let me send that to chat. Okay. Okay, where's the chat? Okay. Oops, sorry, I saw the private message. Private messages to me are not private anymore. How do I send to everyone? Okay, everyone. Yeah. Okay, so I'll follow up on the private question. Maybe my colleagues can do that too. So they're actually maybe better able to direct to you. Okay, so last part. So I'll just wrap up here. So what you saw is basically a flavor of one of these classes, Designing Intelligent Edge Computing, which is in here. So notice where it is. It's actually, oh, it's a second cert. Okay, that's not how it's speak. It's one of the specialist cert. So this is the fundamental one, and this is the fundamental one. So this is actually a more advanced cert. So people taking this are actually in their second semester already. This is the class we are here currently, right? So if you felt a little bit overwhelmed by what I was talking about, it's very normal. Okay. So we are talking about edge compute systems and machine learning. So the last day was more about the self-learning part, right? Because we covered these already. And I think that's it. The feedback, here's it's the same URL. Yes, it's the same URL. So I will just scan this one. And for those who are interested in giving us feedback, go ahead and do this. And you will share the slides and all that through this. Okay, one last chat. Okay, yeah, Gary is my colleague. So so thank you everybody for your time. I know it's a and also thank my class here. They are patiently, silently not asking any questions because they know there's a lot of content. So maybe we'll see you in one of these courses and in ISS. Okay, so I'm gonna sign off. All right, thanks. Okay, mute.